we've just got a voltage source, an AC voltage source, a resistor, and then from that we've got a current. If we look at our waveforms, I'm going to plot the voltage of the resistor first. Or let's just call it the source. And I'm going to plot the current on the same diagram. Right, we can see that the current and the voltage are in phase. Let's look at the power. Right. Sorry. Right, so the power is equal to your voltage multiplied by your current. Right, so it's the voltage across the resistor multiplied by the current through it. In this case, the voltage is the same. Right, so that's in watts. If we look at our apparent power, remember it's a vector. In this case, your apparent power S is equal to P, and that's in VA. Right, let's look at a capacitor in a similar sort of situation. Let's do the same thing. Plot our voltage. Our current won't be in phase. It'll be 90 degrees leading. Right, so in this case, we only have reactive power. That's given in VAR. Let's look at combining a couple of them. We'll put a resistor and a capacitor in series. Let's do the same thing. This time, let's see if you can see the yellow. I'm actually going to start with the current. Next, I'm going to plot my voltage of my across my resistor. Sorry. Right, what you can see is that it's in phase with the current. Next, I'm going to plot my voltage across the capacitor. And it's out of phase with the current. So your resultant voltage will be the sum of those two, which will be somewhere in between. Whoops. Let's have a look at our powers. Right, so we start with our real power. P equals to V RI. They're vectors, so I can add our reactive power over here. Oops, it's meant to be purple, sorry. Right, so you're all happy with that? Assume so. Okay, let's go into one last circuit. Right, in this case, we've got a series connection of a resistor, inductor, and capacitor. I'm not going to draw out the voltages here because it's going to get a little bit complicated. But what I am going to do is I'm going to go straight for the power plot. Start with our real power. We can look at our capacitive reactive power. QL is equal to VLI. We can also look at our capacitive reactive power, which is VCI. Right. So total apparent power will be the sum of all of that. So what you can see with the inductive and capacitive reactive powers, these imaginary powers, that they sort of cancel each other out. They're in opposite directions. So under certain cases, if they're going to cancel each other out, then your apparent power is equal to your real power. So what I found in the practical is that a lot of students had confused real power, reactive power, and apparent power. They were referring to your QC, whoops, here as real power. Okay, let's move on to stop sharing this. I'm not sharing my screen. All right, again, I've got some circuits up here so that you can see that I'm not really lying to you. Right there, you can see your voltage is in phase. It's the same voltage. If you looked at the current, it's also in phase. So the yellow is your source voltage, the green is the voltage across the resistor, the blue is the current through the resistor. Right, same thing here. Your yellow is your voltage of your source, your blue is your current of your capacitor. I'm going to skip this one here because you're getting the concept, I'm sure. And we'll come back to this again a little bit later. Right. So let's look at this voltage source. I've got an amplitude of 10 volts, a frequency of 50 hertz. I'm just plotting. Let's just plot the voltages first. Right, I think one of them is the wrong way. Let me just reverse it again. So you'll agree that it's the same current going through the circuit. That's the green current. If you look at the voltage across your resistor, it's in phase. If you look at your voltage across your capacitor, it's out of phase with the current. And if you look at your voltage across the inductor, it's also out of phase. I think the polarity was wrong. That's better. No, it's not. All right. The sum of those would still equal the voltage of the source Vs. So let's look at the series resonant and just understand it a little bit. So resonance is a phenomena where your reactive power moves from your capacitor to your inductor. It is something that you actually did in a second year practical. What you can see here is that resonance is dependent on your frequency, and that's because your impedances are dependent on your frequency. So let's just assume 50 hertz. We want a resonant peak there. We can set the equation such that we get the resonance. Resonance won't occur anywhere else. So if you look at the plot here, and you just look at the voltages, just do that quickly. If you just take a look at those voltages there, we've got 7 RMS at the source. Your variable inductor hardly has a voltage across it. All the voltages dropped across the capacitor. Your resistance doesn't have much either. So it's not resonating. So the idea of the series resonance circuit is because we test capacitive loads, that we can increase the voltage across that load by using a variable inductor. So normally we need very large transformers with enough power and voltage to provide. But the key to the series resonance is that we don't need as much power. Some advantages: it produces a pure 50 hertz sine wave. So it's not going to put harmonics onto the system because it's only resonating at 50 hertz. We'll look at the power requirements just now. It's simple and compact. Right, so if we've noted that the current is the same. If we take Kirchhoff's voltage law and just look at the voltage here, so VC, there's a voltage divider here. Ultimately, we'll end up with an equation VC, the voltage across the capacitor, is equal to V divided by omega CR. What you need to be careful of here is that you don't mix up VC and V. Don't put them the wrong way around. So what I'm saying is that at resonance, and we can try this out, just with some values, we've made R equal to 100, C equal to 100 nanofarads, and we've got a voltage of V. If we plug that into the equation, we get a voltage of 3000 volts out. If you look at your circuit again, 10 volts in, 3000 volts out. So depending on how you did your practical, do you believe me or not? A thumbs up will do. One person, two people believe me. Right, I'm just going to do a quick equation and determine our inductance. And then we can have a look at the circuit in the circuit package. Right, so for resonance to occur, I need my inductance to equal 101.32. Right, so at the moment, you can see that it's not resonating. There's no high voltages there. Let's just put it at 90 and see what happens. Right, you can see that it's getting close to resonance now. You've got an input voltage of 7. Your voltage of your inductor is 42. Your voltage of your capacitor is 47. Right, if we have a look now, it's much closer to resonance. We've got 7 volts RMS in, 66 volts out across your inductor, and 66 volts across your capacitor. Just going to adjust it slightly and see what we get. Right, I'm not sure why it's not quite resonating to the same levels, but it's okay. You can see the concept. Low voltage in, high voltage out. So the question is, what is the output power? What is the rating here? Is the power here? Doesn't it get cancelled by the reactive power here? Yeah, it does, because they're in opposite directions. So the input power is actually just the real power across the capacitor, across the resistor, or through the resistor. I refer back to here. The power requirements are less. Because it's resonating, you don't need the high power of a normal transformer. So again, let's draw it out a little bit. Let's say we've got a 100 nanofarad capacitor. Let's say it's representing an 88 kV cable. Right. So that's the V line. Our V naught would be equal to 88 divided by 3. That's 50 kV. Those folk that did look it up properly will normally find that it's at 2U naught. I also would have accepted the power frequency withstand voltage in the practical. The lightning impulse withstand voltage is a lightning impulse withstand voltage. It's not an AC voltage. Right, so we need to test this capacitor with 100 kV. So let's look at the power rating. I get 63 milliamps there. Does anybody want to check that and just give me a thumbs up if it's right? So I get a value of 6.3 kVA. I'm going to swap the voltages around so that I can determine my input voltage to get 100 kV across. I get a value of 314 volts. At 100 kV, we know that our current is also 63 milliamps. If we look at our power, P plus JQ, we know at resonance, Q disappears. So total power required in this case is 20 VA. So the point of the series resonant, and the reason you can take it to site better than any other type of transformer, is because the power requirements are less. Does that make sense to everybody?